crucial to the survival of a glacier is its mass balance or surface mass balance, the difference between accumulation and ablation. Climate change may cause variations in both temperature and snowfall, causing changes in the surface mass balance. Changes in mass balance control a glacier's long-term behavior and the most sensitive climate indicators on a glacier. From 1980 to 2012, the mean cumulative mass loss of glaciers reporting mass balance to the World Glacier Monitoring Service is -16 meters. This includes 23 consecutive years of negative mass balances. A glacier with a sustained negative balance is out of equilibrium and will retreat, while one with a sustained positive balance is out of equilibrium and will advance. Glacier retreat results in the loss of the low elevation region of the glacier. Since higher elevations are cooler than lower ones, the disappearance of the lowest portion of the glacier reduces overall ablation, thereby increasing mass balance and potentially re-establishing equilibrium. However, if the mass balance of a significant portion of the accumulation zone of the glacier is negative, it is in disequilibrium with the local climate. Such a glacier will melt away with a continuation of this local climate. The key symptom of a glacier in disequilibrium is thinning along the entire length of the glacier. For example, Eastern Glacier will likely shrink to half its size, but at a slowing rate of reduction, and stabilize at that size, despite the warmer temperature, over a few decades. However, the Grinnell Glacier will shrink at an increasing rate until it disappears. The difference is that the upper section of Eastern Glacier remains healthy and snow-covered, while even the upper section of the Grinnell Glacier is bare, melting and has thinned. Small glaciers with shallow slopes such as Grinnell Glacier are most likely to fall into disequilibrium if there is a change in the local climate. In the case of positive mass balance, the glacier will continue to advance, expanding its low elevation area, resulting in more melting. If this still does not create an equilibrium balance, the glacier will continue to advance. If a glacier is near a large body of water, especially an ocean, the glacier may advance until iceberg calving losses bring about equilibrium. Measurement methods. Mass balance. Mass balance is measured by determining the amount of snow accumulated during winter, and later measuring the amount of snow and ice removed by melting in the summer. The difference between these two parameters is the mass balance. If the amount of snow accumulated during the winter is larger than the amount of melted snow and ice during the summer, the mass balance is positive and the glacier has increased in volume. On the other hand, if the melting of snow and ice during the summer is larger than the supply of snow in the winter, the mass balance is negative and the glacier volume decreases. Mass balance is reported in meters of water equivalent. This represents the average thickness gained or lost from the glacier during the particular year. To determine mass balance in the accumulation zone, snowpack depth is measured using probing, snowpit or crevasse stratigraphy. Crevasse stratigraphy makes use of annual layers revealed on the wall of a crevasse, akin to tree rings. These layers are due to summer dust deposition and other seasonal effects. The advantage of crevasse stratigraphy is that it provides a two-dimensional measurement of the snowpack layer, not a point measurement. It is also usable in depths where probing a snow pits are not feasible. In temperate glaciers, the insertion resistance of a probe increases abruptly when its tip reaches ice that was formed the previous year. The probe depth is a measure of the net accumulation above that layer. Snow pits dug through the past winter's residual snowpack are used to determine the snowpack depth and density. The snowpack's mass balance is the product of density and depth. Regardless of depth measurement technique, the observed depth is multiplied by the snowpack density to determine the accumulation in water equivalent. it is necessary to measure the density in the spring as snowpack density varies. Measurement of snowpack density completed at the end of the ablation season yield consistent values for a particular area on temperate alpine glaciers and need not be measured every year. In the ablation zone, ablation measurements are made using stakes inserted vertically into the glacier either at the end of the previous melt season or the beginning of the current one. The length of stake exposed by melting ice is measured at the end of the melt season. Most stakes must be replaced each year or even midway through the summer. Net balance. Net balance is the mass balance determined between successive mass balance minimums. This is the stratigraphic method focusing on the minima representing a stratigraphic horizon. In the northern mid-latitudes, a glacier's year follows the hydrologic year, starting and ending near the beginning of October. The mass balance minimum is the end of the melt season. The net balance is then the sum of the observed winter balance normally measured in April or May and summer balance measured in September or early October. Annual balance. Annual balance is the mass balance measured between specific dates. The mass balance is measured on the fixed date each year, again sometime near the start of October in the mid-northern latitudes. Geodetic methods. Geodetic methods are an indirect method for the determination of mass balance of glacier. Maps of a glacier made at two different points in time can be compared, and the difference in glacier thickness observed used to determine the mass balance over a span of years. This is best accomplished today using differential global positioning system. Sometimes the earliest data for the glacier's surface profiles is from images that are used to make topographical maps and digital elevation models. Aerial mapping or photogrammetry is now used to cover larger glaciers and ice caps such found in Antarctica and Greenland. However, because of the problems of establishing accurate ground control points in mountainous terrain, and correlating features in snow and where shading is common, elevation errors are typically not less than 10 meters. Laser altimetry provides a measurement of the elevation of a glacier along a specific path, e.g., the glacier centerline. The difference of two such measurements is the change in thickness, which provides mass balance over the time interval between the measurements. Again, a good method over a span of time, but not for annual change detection. The value of geodetic programs is providing an independent check of traditional mass balance work by comparing the cumulative changes over 10 or more years. Mass balance research worldwide. Mass balance studies have been carried out in various countries worldwide, but have mostly conducted in the Northern Hemisphere due to there being more mid-latitude glaciers in that hemisphere. The World Glacier Monitoring Service annually compiles the mass balance measurements from around the world. From 2002 to 2006, continuous data is available for only 7 glaciers in the Southern Hemisphere and 76 glaciers in the Northern Hemisphere. The mean balance of these glaciers was its most negative in any year for 2005-06. The similarity of responsive glaciers in western North America indicates the large-scale nature of the driving climate change. Alaska. The Taku Glacier near Juneau, Alaska has been studied by the Juneau Icefield Research Program since 1946, and is the longest continuous mass balance study of any glacier in North America. Taku is the world's thickest known temperate alpine glacier, and experienced positive mass balance between the years 1946 and 1988, resulting in a huge advance. The glacier has since been in a negative mass balance state, which may result in a retreat if the current trends continue. The Juneau Icefield Research Program also has studied the mass balance of the Lemon Creek Glacier since 1953. the glacier has had an average annual balance of -0.44 meters per year from 1953 to 2006, resulting in a mean loss of over 27 meters of ice thickness. This loss has been confirmed by laser altimetry. Austrian glacier mass balance. The mass balance of Hintereresferner and Kesselwindferner glaciers in Austria have been continuously monitored since 1952 and 1965 respectively, having been continuously measured for 55 years. Hintereresferner has one of the longest periods of continuous study of any glacier in the world, based on measured data and a consistent method of evaluation. Currently this measurement network comprises about 10 snow pits and about 50 ablation stakes distributed across the glacier. In terms of the cumulative specific balances, Hintereresferner experienced a net loss of mass between 1952 and 1964, followed by a period of recovery to 1968. Hintereresferner reached an intermittent minimum in 1976, briefly recovered in 1977 and 1978 and has continuously lost mass in the 30 years since then. Total mass loss has been 26 meters since 1952. Sonnenblick's glacier has been measured since 1957 and the glacier has lost 12 meters of mass, an average annual loss of -0.23 meters per year. New Zealand. Glacier mass balance studies have been ongoing in New Zealand since 1957. Tasman Glacier has been studied since then by the New Zealand Geological Survey and later by the Ministry of Works, measuring the ice stratigraphy and overall movement. However, even earlier fluctuation patterns were documented on the Franz Josef and Fox glaciers in 1950. Other glaciers on the South Island studied include Ivory Glacier since 1968, while on the North Island, glacier retreat and mass balance research has been conducted on the glaciers on Mount Ruapehu since 1955. On Mount Ruapehu, permanent photographic stations allow repeat photography to be used to provide photographic evidence of changes to the glaciers on the mountain. Over time, an aerial photographic survey of 50 glaciers in the South Island has been carried out for most years since 1977. The data was used to show that, between 1976 and 2005 there was a 10% loss in glacier volume. North Cascade Glacier Mass Balance Program. The North Cascade Glacier Climate Project measures the annual balance of 10 glaciers more than any other program in North America, to monitor an entire glaciated mountain range, which was listed as a high priority of the National Academy of Sciences in 1983. These records extend from 1984 to 2008 and represent the only set of records documenting the mass balance changes of an entire glacier cloud range. North Cascade Glacier's annual balance has averaged -0.48 meters from 1984 to 2008, a cumulative thickness loss of over 13 meters at 20 to 40% of the total volume since 1984 due to negative mass balances. The trend in mass balance is becoming more negative, which is fueling more glacier retreat and thinning. Norway Mass Balance Program. Norway maintains the most extensive mass balance program in the world and is largely funded by the hydropower industry. Mass balance measurements are currently performed on 15 glaciers in Norway. In southern Norway, 6 of the glaciers have been measured continuously since 1963 or earlier. and they constitute a west-east profile reaching from the maritime Alfotbreen Glacier, close to the western coast, to the continental Grasubbreen Glacier in the eastern part of Jotunheimen. Storbreen Glacier in Jotunheimen has been measured for a longer period of time than any other glacier in Norway, starting in 1949, while Engebbreen Glacier at Svartisen has the longest series in northern Norway. The Norwegian program is where the traditional methods of mass balance measurement were largely derived. Sweden's Stor Glacier and the Tafala research station in the Kebnekaise region of northern Sweden is operated by Stockholm University. It was here that the first mass balance program was initiated immediately after World War II and continues to the present day. This survey was the initiation of the mass balance record of Stor Glacier and Glacia, and constitutes the longest continuous study of this type in the world. Stor Glacier has had a cumulative negative mass balance from 1946 to 2006 of -17 meters. The program began monitoring the Rabbits Glacier in 1982, Ryukogetna in 1985, and Marma Glacier in 1988. All three of these glaciers have had a strong negative mass balance since initiation. Iceland Glacier Mass Balance. Glacier mass balance is measured once or twice annually on numerous stakes on the several ice caps in Iceland by the National Energy Authority. Regular pit and stake mass balance measurements have been carried out on the northern side of Hofsjökull since 1988 and likewise on the Thrandarjökull since 1991. Profiles of mass balance have been established on the eastern and southwestern side of Hofsjökull since 1989. Similar profiles have been assessed on the Tungnajökull, Dyngjujökull, Kullrakvislejökull and Broajökull outlet glaciers of Vatnajökull since 1992 and the Aubackajökull outlet glacier since 1991. Swiss Mass Balance Program. Temporal changes in the spatial distribution of the mass balance result primarily from changes in accumulation and melt along the surface. As a consequence, variations in the massive glaciers reflect changes in climate and the energy fluxes at the Earth's surface. The Swiss glaciers Grise in the Central Alps and Silvretta in the Eastern Alps have been measured for many years. The distribution of seasonal accumulation and ablation rates are measured in situ. Traditional field methods are combined with remote sensing techniques to track changes in mass geometry and the flow behavior of the two glaciers. These investigations contribute to the Swiss Glacier Monitoring Network and the international network of the World Glacier Monitoring Service. United States Geological Survey. The USGS operates a long-term benchmark glacier monitoring program which is used to examine climate change, glacier mass balance, glacier motion, and stream runoff. This program has been ongoing since 1965 and has been examining three glaciers in particular: Gulkana Glacier in the Alaska Range and Wolverine Glacier in the Coast Ranges of Alaska have both been monitored since 1965, while the South Cascade Glacier in Washington State has been continuously monitored since the International Geophysical Year of 1957. This program monitors one glacier in each of these mountain ranges, collecting detailed data to understand glacier hydrology and glacier climate interactions. Geological Survey of Canada Glaciology Section. The GSC operates Canada's glacier climate observing system as part of its climate change geoscience program. With its university partners, it conducts monitoring and research on glacier climate changes, water resources and sea level change using a network of reference observing sites located in the Cordillera and the Canadian Arctic Archipelago. This network network is augmented with remote sensing assessments of regional glacier changes. Sites in the Cordillera include the Helm, Place, Andre, Cascade-Quelch, Hague, Peltoms, Ram River, Castle Creek, Quadacha and Bologna Creek glaciers. In the Arctic archipelago include the White Baby and Grise glaciers and the Devon, Megan, Melville and Agassiz ice caps. GSC reference sites are monitored using the standard stake-based glaciological method and periodic geodetic assessments using airborne lidar. Detailed information, contact information and database available here. Helm Glacier and Place Glacier have lost more than 20% of their entire volume since 1980. Peyto Glacier is close to this amount. The Canadian Arctic White Glacier has not been as negative since 1980. Bolivia Mass Balance Network. The Glacier Monitoring Network in Bolivia, a branch of the Glacier hydrological system of observation installed throughout the tropical Andes Mountains by IRD and partners since 1991, has monitored mass balance on Zongard, Chacaltaya and Charquini glaciers. A system of stakes has been used, with frequent field observations, as often as monthly. These measurements have been made in concert with energy balance to identify the cause of the rapid retreat and mass balance loss of these tropical glaciers. PTAA Mass Balance Model, a recently developed glacier balance model based on Monte Carlo principles, is a promising supplement to both manual field measurements and geodetic methods of measuring mass balance using satellite images. The PTAA model requires only daily observations of precipitation and temperature collected at usually low-altitude weather stations, and the area-altitude distribution of the glacier. Output a daily snow accumulation and ablation for each altitude interval, which is converted to mass balance by Bn equals Bc bar. The model has been tested for 8 glaciers in Alaska, Washington, Austria and Nepal. Calculated annual balances are compared with measured balances for approximately 60 years for each of 5 glaciers. Linear regression of model versus measured annual balances yields R2 values of 0.50 to 0.60. Application of the model to Bering Glacier in Alaska demonstrated a close agreement with ice volume loss for the 1972 to 2003 period measured with the geodetic method. Determining the mass balance and runoff of the partially debris-covered Langtang Glacier in Nepal demonstrates an application of this model to a glacier in the Himalayan range. Correlation between ablation of glaciers in the Wrangell Range in Alaska and global temperatures observed at 7,000 weather stations in the northern hemisphere indicates that glaciers are more sensitive to the global climate than are individual temperature stations, which do not show similar correlations.